Example number 2.3. Figure A and B show the filled lines of positive and negative point charges respectively. So we all know that for positive charges, electric field lines are always bulging outwards. For negative charges, it is going inside. Here these are coming outside of the positive charge. First thing is, give the sign of potential difference Vp minus Vq and Vp minus Va. Okay, so Vp minus Vq and Vb minus Vp. We are just supposed to give the sign of it. We all know that electric field decreases as we go away from the charge. So at point P, electric field would be somewhat bigger than at point Q. So Vp should be greater than Vq. Okay, so sign of these two should be the positive. Okay. Next is, give the sign of potential energy difference of a small negative charge between the points Q and P and A and B. Q and P and A to B. We are supposed to give the sign of the negative sign of potential energy. Here the potential energy is directly dependent on the potential, or let's just say electric field into potential displacement. So a small negative charge will be attracted towards positive charge. The negative charge moves from higher potential energy to lower potential energy. Therefore, sign of potential energy difference of small negative charge between Q and P is positive. Because it is a negative charge, it is going to attract towards the P. From Q to P, it is going to get attracted. So that is going to be a positive. Similarly, potential energy at A is bigger than the potential energy at B. Hence, the signs of potential energy difference is positive. C. Give the sign of work done by the field in moving small positive charge from point Q to P. Here we are supposed to do work in the opposite direction of the force. In moving small positive charge from Q to P, work has to be done by external agency against electric field. Therefore, work done by the field is negative. D. Give the sign of work done by external agency in moving a small negative charge from B to point A. Okay, this is also seen as the C part of it, since it is also a negative charge and we are supposed to bring from point B to point A. Okay, so work done by external energy agencies is positive, while work done by the field is negative. E. Does kinetic energy of a small negative charge increases or decreases in going from point B to A? Okay, due to the force of repulsion on a negative charge, velocity decreases and hence kinetic energy decreases in bringing from B to point A. Since we are talking about this negative charge, and at the center also there is a negative charge. Two negative charges repel each other, therefore there has to be a repulsion, and due to this repulsion velocity is going to be decreased for the constant force. Okay, so these are the questions. Next is equipotential surfaces. Equipotential surfaces means surface with the constant value of potential on the entire surface. For examples, all conductors have equipotential surface. That means as you give any charge into it, it is going to distribute it in such a way that there is an equal distribution of charges. So right now we are talking about this equipotential surface, and for equipotential surface consider a charge, small charge plus q, and the electrostatic or equipotential surfaces around it. Can the potential around it is going to be is equal to 1 upon 4 pi epsilon naught q upon r, because r is the distance from these. So if I am considering the r radius in 3 dimensions, this could make a shell kind of structure around this plus q charge, and on this entire shell there is an equal potential. Okay, so this we have already discussed in previous lectures. In this also we are saying, so this is, and the direction of electric field in this entire shell is going to be normal to the surface itself. For equipotential surfaces, electric field direction is always normal to the surface. Electric field perpendicular to equipotential surface passing through that point. Equipotential surface which is passing through this point. Suppose I am talking about this P point. So at P point it is normal to the electric field. Something similar to that we have already seen while we were representing electric field lines or force lines due to a positive charge plus q. We were showing this positive electric field lines bulging outwards, and it was always normal to the surface. So we can also discuss it in this way. What if electric field lines, or let's just say equipotential surfaces, are not perpendicular to the electric field lines are not perpendicular to the equipotential surfaces. So in that case, the angle between these two would be anything except 90 degrees, right? So in that case, the surface is going to be contributing something which cannot be expressed in the definition of equipotential surface. Another thing can be understood with the help of this. If I am giving certain charges to this conducting shell, then these charges are eventually going to settle down on entire surface of it. I am just giving charges to this particular point. I am not going to move these charges through this entire surface, but it is being done by itself. That means that for the work done, work should be done in moving it away. For equipotential surface, it is work done is equal to 0, because electric field is perpendicular to the surface. Okay. Relation between field and potential. Here we are talking about electric field and electrostatic potential. Obviously, electrostatic field itself, it will be intensity also, and the potential. electric field, there is change in V. Okay, what change? Delta V change. Let P be on the surface of B. On the surface of P, there is a P point. Delta L is the perpendicular distance of A from P. Okay, so this is the perpendicular distance AP, which is equal to delta L. Consider a unique positive charge is moved along these, that is AP, along AP line from B to A. This is the B to the point A. Because electric field is in this direction, so force would be in this direction, F would be in that direction. So work done, if we want to calculate work done with help of potential, then we all do know that we are supposed to do work in the opposite direction of force. This is the direction of A, that means it is the direction of F, and we are supposed to do work in the opposite direction, that means from B to A against electric field E. So work done is what? Work done is nothing but force into displacement. That is force is equal to, again force is equal to Q multiplied by E into S. Again over here we are talking about unit positive charge. That means Q is equal to 1. That means E dot delta S. Over here displacement delta is nothing but delta L. So we substituted and we got the work done. Okay. Again work done is also a change in potential, but work done, try to recall this, work done is equal to V initial minus V final. Initially the potential was V, finally the potential was V plus delta V. So we will substitute the value of VA minus VB and then we get work done, which is equal to E delta L. These two are going to cancel each other, therefore delta magnitude of E is equal to negative delta V upon delta L. Since delta V is negative, that means delta V is equal to negative delta V, because delta V itself is a negative. Okay, so delta magnitude of E is equal to negative delta V upon delta L. So to cancel this sign, we can also write change in V, that could be magnitude of delta V upon delta L. Okay, so this is the important formula that you should remember. Okay.